So a quick recap, we talk about force and moment. And force and moment are things that we are going to discuss in this course a lot, basically. And we said the whole course is all these external forces and moments, they create some internal stresses, and our goal is to calculate those stresses in a member. Okay, that's the plan. And this is one step before designing something. So force, we know it's a scale, it's a vector, right? It needs magnitude and it needs direction. When we apply a force to something, let's say to this wrench here, it creates basically a turning action. It also creates a turning action. That turning action, like here, when this guy applies the force to this wrench, it turns to, basically, it wants to rotate this pipe, basically. So this turning action, we call it a moment, right? And we show it by M. Also, another name, common name is torque, right? Moment or torque. So, and mathematically, we said, if you look at the pictures, like on the left side, at the bottom, this one, which shows the 3D, basically as a general picture, we have the force F, and we are interested to find out the moment about point A. Remember, when we talk about moment, always it is about an axis, right? Here, again, look back at this pipe. We want to rotate this pipe around this vertical axis, all right? But it's easier for us when we talk or when we teach to say just a point, right? Like here, I just saying, I'm taking the moment about point A. But in fact, whenever we talk about the moment, it's about an axis, like here, which you can see it, right? I apply a force to this plate. Imagine we have a plate, weird shape, and we want to rotate it about point A. Imagine point A is like a door hinge or something, like a pin or something, right? Think of a 3D, basically, image. Like this is your axis, or let's say and this one, and let's say this one, X, Y, and Z axis. Right, so we define moment M as R cross F. And we said that R is a vector. R is a vector that connects A to the point that we apply the load, like this point. Let's call it point B, all right? And F also, we know, is a vector. These two, we are not directly multiplying them together. It's a cross product, right? So remember, this is a cross product. If, again, you forgot this cross product, dot product, maybe just quickly check it on YouTube or Google it, or go back and check your notes from one of your math courses, right? So, but again, as I said on Tuesday, we are not going to use this vector form a lot. Instead, what we are going to do, we say that, well, we learned that R cross F gives us like the magnitude R multiplied by F multiplied by sine alpha. This is the definition of cross product. Okay, when we have two vectors, we cross them together, we multiply them together by a cross product. This is the definition. RF sine basically alpha. Again, something from your math course. Let's say I have two vectors here, V1 and V2, and the angle between them is alpha. So you learn that the cross product V1 cross V2 is equal to the size of V1, size of V2, sine alpha, right? And this gives us a vector, which we learn this vector is basically perpendicular to the plane of these two V1 and V2. Let's say if I have these two in this plane, right? This is a plane. Then the cross product, let's call it V, right? This V is this basically vector, all right? The same concept here. I have here M as a vector, right? You see, it's a vector coming out of the plane, right? It's a cross product like this V. But for simplicity, we just show it by a rotating, basically, or a curve, maybe force or something, right? Just to show it for simplicity. And it is a vector, like M is a vector. So if I simplify these things, I can write down R sine alpha, right? The same things multiplied by F. But we know this R sine alpha is equal to D, basically, which D over here in this triangle is this distance, right? See, if this angle is alpha, if this angle is alpha, this angle also is alpha, and this D is equal to R sine alpha. So then we decide to simplify things, and we decide to write down it as simply D multiplied by F. But we remember that this D is the perpendicular distance. As I said on Tuesday, on the last day, you draw the line of action, all right? The line of action, we call it the line of action. And basically, D is the perpendicular distance between the point that we are interested to take the moment to this line of action is D, right? So, and again, as I said on Tuesday, 99% of the problems we are dealing with in engineering, we can simplify them to 2D problems, although we live in a 3D world, but most of problems, engineering problems, we can simplify them to 2D problem. Like this wrench that I'm showing at the top, it is a 3D problem, but in fact, I can treat it on a plane of where the wrench is, right? Similar to that concept, from now on, we just deal with 2D problem in MEC 260. We don't care about this cross product or thing, and we simply use this last formula for that we have M about point A is F multiplied by D. All right, this is what we discussed on Tuesday. And also we said that, remember, the unit for force is Newton or pound, and for distance it can be inch, it can be centimeter, millimeter, and so on. So the unit then for moment can be Newton meter, it can be Newton millimeter, Newton centimeter, or pound inch, pound foot, and so on, right? And also we decided for a convention. We decided for a convention, so then we can understand each other better, right? So we said that this force, this turning, when we apply a load like this wrench, either we want to rotate something clockwise or we want to rotate it counterclockwise. So counterclockwise or clockwise. So we decided to make our life easier, instead of every time writing clockwise, counterclockwise, and being careful about which direction it was. Anytime a rotation is counterclockwise, we consider it positive. And anytime it is clockwise, rotating like your clock handle, it is negative. If it is counterintuitive, remember, I said we use the right hand rule, and basically using the right hand rule, it's customary to use the counterclockwise as a positive sign. All right. So it was something that we discussed on Tuesday, very simple, but we are going to repeat them a lot by solving different problems, so you get used to it in this course. And it's a little bit different than your Physics 170, because over there you probably use a lot of vectors without getting a sense of these moment and forces, but here you need to shift your mindset a little bit, and you need to understand how things are reacting when you're creating a moment, how it's tend to rotate something, and so on. All right? So let's get to the main topic of today, which is equilibrium. So as I said on Tuesday in this course, everything is in a stationary position. So to have no motion, right? If we are interested in analyzing motion and rotation and spinning things, we go to a dynamics course. In this course, everything is balanced. All the forces and all the moments are balanced. So that's the definition of equilibrium, right? So that's the definition. So if I turn this definition to mathematical equations, it is called equilibrium condition or equilibrium equation. Like, let's see in this image that I'm showing here on the right side, right? We have a bunch of stone and this nice triangular shaped stone. Somebody somehow could balance it on the top of this stone. So we know, let's say this stone has a weight. Let's call it, and this one also has another weight. And so maybe that's the center of gravity of the first one. This one is the center of gravity of the second one. Let's say call it W1, and this one is W2. And maybe also this basically long stone, also it has maybe a center of gravity, maybe somewhere, let's say around here. That's the center of gravity for this guy. And it also has a weight. Or maybe if we are lucky, the center of gravity is exactly at this tip point of this triangle, okay? And let's say the weight of that guy is W3. So since everything is balanced, like everything is staying there, it means that like this W1 and W3, they want to rotate these things basically counterclockwise, right? They want to rotate it counterclockwise, but this W2 is counterbalance them and keep everything's like in horizontal position. So we see this moment they are canceling out each other. Also, when we see that we have this W1, W2, and W3, there must be something to cancel these loads. Otherwise, these things are going to fall down on the ground, right? So in that sense, then we say there must be like a big force here, a reaction force here from the support. So let's call it support. And there must be a reaction from this support. So all these forces must be balanced. Also, we know that there must be friction, right? Because two stones on top of each other, there must be friction. So let's say I have maybe a friction over here. Sorry, let me get back to, yep. Okay, so I have also friction. So maybe there is one friction here. I call it F1. Maybe there is another friction over there. And maybe there is a big friction also here. We don't know the numbers or direction, but for now, it doesn't matter. We call this one maybe big FF, F friction. This is maybe F1 and this one F2. So all of these forces and basically moment must be balanced. So this brings us to the equilibrium condition. We say if all the forces and all the moments are balanced, then sum of the moment, the total moment must be equal to 0, right? If I take all the moments in this picture, it must be 0. And also, sum of all the forces must be 0. If I add up all these forces in a vector form, of course, the sum must be 0. So I can simplify it or break it down to x and y, like in this problem. So I can write it then. All the forces in x direction must be 0, and sum of all the forces in y direction must be 0. So basically, if I write down all of them here, sigma fx equal to 0, sigma fy equal to 0, and sigma m equal to 0. These three equations, they are equilibrium equations. And for the rest of this course, these are basically the fundamental equation that we are going to use it in different problems, right? So, but for us, in order to solve a problem, we need to start figuring out the forces, right? Some forces like this W1, W2, or W3, we call them external forces. We know that they exist, we know their direction. But we are also interested in finding these reaction forces, right? Because we want to do the design. Of course, not here for this stone, but later we want to design a support. So we are also interested in finding this support. How we can find basically the reaction forces and using this formula, it's a process which we call it free body diagrams, all right? Let me write it down here. Free body diagram, which in short, we are going to write it down FBD, okay? And it's going to be your friend for the rest of this course. And you need to master these FBD things if you want to solve a problem correctly. In fact, 90% of solving a problem correctly in this course, it comes back to this FBD or free body diagram. But what it is, it's super, super simple. As the name implies, we want the main body to be free from its support. So we remove all the supports and we draw the reaction forces or moments. And this is something that we call it a free body diagram. Like in this example of this stone, the free body diagram. So the main body is this big stone here. This is the big stone. So I draw basically the external loads, right? I have like these frictions and maybe this one friction. And then, also I have this weight W3, right? And then what I have here is the reaction force. All right, let's call them maybe F, Y, and or maybe whatever you want to call them. Let's say if the name of this support is S, let's call it SY and SX. All right, so this is W1, F1, W3, W2, and F2. This is in fact a free body diagram. Okay, so then we use this free body diagram. We assume that we have all this distance that we want to do some calculation. Let's say I have this distance A, B, C. And so I have the geometry, I have the force diagram, and then which we call it FBD, and we use it plus these basically three simple formula to find the reaction forces, like in this case, to find Sx and Sy, okay? So since this free body diagram is an important thing, let's look at the common supports that we may encounter in design, right, in reality. So we start with a very, very simple one, a cable. A cable is a support something that's hanging from somewhere, or we want to keep something in a certain position. Like here in this, the first one, we use a cable. Remember when we show in this course something like that, it means a wall or ground, right? Wall, or like in this case, it is ground. It is fixed. Sometimes we show it like these shadow things, or sometimes in drawing we show it with like this simple hash, okay? Whenever you saw this one, it means basically ground. It means fixed, it's not gonna move. It's solid and fixed, okay? So over here I have a cable. If I wanna draw the free body diagram for this, whatever shape it is, like this main part, I need to cut this cable basically. I need to free it from this support basically. And this cable, it's very simple. Everybody knows a cable can apply just one sort of force, which is a tension, right? So Then simply the free body diagram for this case, I'm drawing it over here. So this is my, maybe this is just, it seems to be a beam or something, which we don't know about the rest of it, but it's just a force, and let's say we call it T. Okay, this is the free body diagram, and then the geometry of it, of course, is to stay as we see it, like this angle is theta, right? Yeah, over here it shows theta. So that's very simple and intuitive, right? So the second one, imagine that you have like maybe a ball or maybe a big stone or something, a big round things, and it is on a surface, and it says it's a smooth surface. In this course, when we say smooth, it means that you ignore basically friction, right? You don't need to be worried about friction. But if you say a rough surface, you need to be careful that it means there is friction. So, and most likely you saw this one in your physics course. When you have a surface, the surface apply a normal load. Let's call it N, right? It's very, again, simple. So then the free body diagram, if I draw, let's say the ball or whatever it is here, is just one force, which we call it N, or whatever you like to call it, okay? But be careful, this N is basically, this N has to be perpendicular to this line, which is the cotangent of these two surfaces, right? This line is the cotangent, and this N has to be perpendicular basically to that line. So the same things, but this time we have a rough surface. So if it is a rough surface, then I have to be careful that I have two forces. They are perpendicular to each other. N, and this one, maybe we call it F. So then the free body diagram, so this is the things, whatever it is, I have N and I have F, right? N and F. So again, so far as you see, nothing new, everything is something that you've seen before, all right? So let's go to the next one, which is a roller, basically, a roller support. A roller, like the shopping cart that you have, is just a roller. So a roller, what sort of support it is? So we know when we have a roller, the purpose of using a roller, like just look at the first one, which is a familiar one, right? You've seen it before in a shopping cart, maybe, right? So this first one, the role of this roller is basically to let you move it freely left and right, right? You can move it up, but this roller doesn't let you to press it down, basically, right? Move it down. So in fact, the reaction that this roller applies here is just one vertical or reaction load like that one. So if I want to draw the free body diagram for this one, this is the main part. Again, this link. Remember, we draw the free body diagram for the main part, and the free body diagram is just one force here, which we can call it, let's say, F or whatever. Okay, this is the free body diagram. So there are a version of this roller like this one. This is just, again, a schematic, but sometimes maybe outside you see these sort of things. So you see like a triangular shaped bracket or plate, which underneath of it there are some small cylindrical roller, right? The second one. This is basically the same concept. The force, the reaction force is just one force. And sometimes, for just simplicity, instead of showing the whole roller, they just show a portion of it. So if you saw something like this shape, be careful. It doesn't throw you off. It doesn't confuse you. It's just the same concept, right? And then the next one is very similar to the roller. It's more like you put a ball, like a ball bearing or something, like a full ball, maybe a solid ball, underneath of a table or something, not a table, maybe a box, right? So again, you can freely move it to the left and right. You can move it up and not, you can move it up, but you cannot move these things, this box down, right? You can also move these things inside the screen, right? And that's the only difference between this one and the roller. The roller, you cannot move it into the screen. Imagine your screen, you cannot move the roller inside your screen, right? But this one, you can push this box toward your, like inside your screen, or pull it back toward yourself if you're watching your screen, right? So, but since we are in 2D, we don't care about that force. We just say that, well, this box or whatever it is, the free body diagram is just one force here. Let's call it F. So far as you can see, nothing really special. Everybody knows that when you have a cable, the cable apply a tension T. You've seen it in physics, normal force and friction force, the same, right? A roller, well, everybody knows that a roller applies just a reaction force from the ground to the main part. And this guy, the same as roller, it's just apply one load to the box coming from the ground to the box. Okay, let's move to other supports. So the next one, which is very, very common, is a pin support or joint support. People call it pin or joint or simple connection. So there are a variety of names which you're going to see it as we go further and further, these different names. So what it is in fact a joint. It's more like your hinge, like your door hinge, right? So this is again ground. So you fix this triangle to the ground, and at the top of this triangle you have a pin basically, or you have a joint basically, and this link has been joined to that pin. So in other words, you can easily rotate these things left and right. Okay, this is something that we call it a joint. You can move it left and right, but you cannot move these things. You can rotate it, sorry, you can rotate it to the left and right, clockwise and counterclockwise, but you cannot move this link to the left, and or you cannot lift it up or push it down, right? Because it's fixed to the ground. So in other words, the reaction from this pin is going to be, let me erase this one so you don't get confused by this one. So the reaction is going to be like one vertical and one horizontal forces. If I want to draw the free body diagram, then for this link, let's say this is the link, this is the where it has been pinned, right? So it's going to be one horizontal and one vertical force. So let's say if the name of this joint is joint A, then it's customary for us to write this one as AX and write this one as A1. And again, we don't worry about the direction of these for now. We just assume positive direction, but later we will see how we figure out the direction of these reactions, basically. Okay. So the one before last, it's something which we call it a fixed support. Fixed support, you have, let's say, the same link or a rod or a bar, and you fix it to the wall, right? This is the wall, maybe made out of concrete, and you put this lumber or maybe this big steel bar into the concrete, let the concrete to basically solidify, and it has been fixed there. Or maybe you just weld these things to the wall. Maybe the wall is steel and you weld it, or maybe you glue it to the wall. So it's a fixed support. So now this fixed support, unlike the previous one, unlike the pin, you cannot rotate it, right? If you try to rotate it, you cannot, okay? It doesn't have the freedom like that one. Also, you cannot move it to the left or right. Can you? No, because it has been fixed there. You cannot move it up or down, right? You are not allowed to do any of these things. So, and the same with the weld one. So if I want to draw the free body diagram, then simply I say, if this is the bar, then I have one reaction in X, one reaction in Y. Let's call this one again, if this support is A, this is AX, this is AY, and also there is going to be a reaction in a form of a couple, which we talk about couple on Tuesday, right? We said couple is a pure moment. It's a turning force, basically, right? And we call this one MA, all right? So these are the reaction. If somebody wants to bend this beam or whatever, rod or whatever it is, then it's gonna, if he wants to bend it or rotate it, then it's gonna be a reaction MA. Okay? So, and then the last one, it looks a little bit complicated, but it's not really. Let's first understand in what it is. Okay, so from what I can see, I have here a wall and a wall over there, and then I have a rod which has been fixed to these walls, okay? And then I have something like this, these things which can slide freely on this rod, right? This box or whatever it is, it has maybe a hole inside and it can freely move left and right. Then I pin something to this box. Let me try to draw for you the 3D version of it. Let's say this is the box that I'm talking about. Maybe it has a cubical shape. Okay, this is this one, this guy. And then it has like a hole going through all the way there. And then I have this, I put this box inside this rod, basically. So this is the basically a rod, right? And it's coming out of that the other way. Okay, so I can easily move this box left and right, okay, into that rod. And then what I did, I fixed this one to a wall over here. This is the wall. So I fix it there. And also I fix this one to this wall again. Okay, so far it's clear, I guess. So these things, I can easily move it to the left and right, These things with no friction or anything. And then what I did, I attached something, I pinned something like this pin over here. You see this pin over there? I pin something to that things over there. So it is pin over here. So if I pin it over here, if it is just a pin, then it means I can rotate it left and right. So the 3D picture is a little bit ugly. Sorry about that, but hope I could get across here my message, right? So the 2D image, I guess now it makes sense. And later we are going to see this support more, so it's going to become more clear. So don't worry for now. So I can move these things left and right. I cannot move it ups and down, but I can rotate it, right? So then I can rotate it easily. I can move it left and right, but I'm not allowed to move it ups and down. So the free body diagram for this guy is going to be then something like this. Just one reaction force. It may be upward or it might be downward. And then the same concept for this one. This is the same. Instead of just a rod, we use a slot here. Okay? So then the reaction force from this slot is going to be just one reaction forces. And don't worry if you don't understand the last one, because we're going to see it in example and it's going to become more clear. All right, so do you need to memorize this table? No. Why? Because it's common sense, right? It's common sense. Each support creates some sort of reaction. If you are not allowed, for example, in a pin to move it to the left or right or ups and down, it means it creates a AX and AY reaction. A wall, it's obvious. You cannot bend it, and also you cannot move it ups and down and left and right. These sliding things, you can rotate it, you can move it left and right, but you cannot move these things ups and down. That's why there is a reaction like this one. All right? So this is more like a schematic form of these supports. In reality, let's say you have a beam, let's say you have big lumbers, wooden lumbers, and you want to make a beam like and put it on two supports. Like the first support is the pin support, right? It looks like the pin support, and then this one looks like the roller support, right? So in practice, if you look at these things as a 3D image, like the bottom image, you see the bottom image, you see, in fact, this support has two sides, okay? In a schematic, we just show one simple things, one triangular shape with a dot in the middle, okay? It's a schematic for like the one that you saw over here. You see the one that you saw over here, we just show a triangle shape. But here, this is, you have the two sides. And I remove like the basically the lumber on this image on the top right. You see there is a pin and the wood can goes there like this one, and then you put the second support over there, okay? And then the roller support, you see you have the bracket, again, two brackets, and on underneath of them there is this support, all right? So the first one, like this joint, this is joint, right? It's obvious. This one, the reaction that it applies is going to be AX and AY, and this one is just going to be one load. If you want to name this one, this is going to be AX, this will be AY, and this is, let's call it B, which is BY, but since we don't have BX, it is just B. Let me quickly show you same things. Okay, so you see the same image here, right? Just give me a second. Okay, so as you see in this image, I have the beam, right? I build it on a concrete foundation, right? So let's say this joint, let's say if I remove this one, the roller one, let's say gone for now, not that one. Let's say this one, we don't need that one, right? So this one, when I have the pin, if I try to move these things, this lumber to the left or right, I cannot. But if I rotate these things, if I try to rotate it, you see I can rotate it, right? You see I can simply rotate it, but if no matter how much force I'm applying now, if I try to move it to the left or lift it, basically like apply a load to move it up from this point, I cannot. But easily I can rotate it. Why? Because it is a joint. And how the mechanism of this joint is working? Well, you know, it's simple pin, the wood, and then we have the support here, right? This is how then it works in basically in practice when we talk a support. But in your course, we simply, when we draw these things, we draw the schematic. We may just draw a beam like this one. And then for the support, remember, we just show something like that, a triangle with a pin. And this one sometimes just maybe something like that. Or if we have more time, maybe we draw something like that. Okay? Any questions so far? Okay, if there is no question, let's move on. Let's solve some example quickly together and see how we can draw the free body diagram for each of these. Rule number one, when we say free body diagrams, it means we want to open up, remove all the supports. Rule number two, depends on each support, we draw the reaction. Rule number three, do I need to worry about the direction of the reactions? No, we let the math to find out the correct direction, okay? So let's say if I start with the first structure, this is a structure, this is a structure which you will see it later. We'll call it a truss. It's a big structure made out of lots of links, steel links. They join together, but we don't care about the structure. This structure, we apply load P, and it has support A and support B. So from what we learned so far, support A is a pin support. It apply two reactions. We call this one AX, and we call this one AY. B is a roller support, right? Take a look, another look at the support. It's a roller support. A roller support apply just one reaction, and that reaction, remember, it's perpendicular to the surface that the roller has been put there. Okay, so this is the free body diagrams for this structure. As you see, it's really simple, right? Let's look at the second one. Second one, I have a beam here. So this beam, as you see, it has been joined here at B, all right? So B is then a joint. This is like a pin or a joint, right? You see, we can say from the shape of it, it's a pin. And then it leaned just at the corner of A. The question didn't say anything about the friction, so we assume that this point A is smooth, basically, right? And then we have these weird things here, which if you remember on Tuesday, I told you about basically a couple, right? Couple, sometimes we show it like in this form. Like this is the schematic way that people show it. Sometimes we show it like that, and sometimes we show a couple like that. Remember that screwdriver that I showed you? This is just a schematic way to show it. So if you saw something like that, two forces, two small forces, two small arrows, opposite direction, parallel, and the same in a distance, we call it a couple. And sometimes we show it like this M, and sometimes we show it like that. That's about it, okay? But what about the reaction forces? So B is a pin. Pin always, we said, apply two loads. We call one of them Bx and another one By. A, so A basically is more like free support. It applies just a reaction force, right? That's the second one in the image that I showed you. It is 90 degrees here, and it is a reaction from the ground going there. If I move up 2 steps or maybe 3 steps, it's this one, right? When you have a smooth surface, you have a normal reaction, right? So that's the free body diagram then for this beam. Sometimes if we don't want our pictures to get messy, so I suggest you draw the main structure like this beam here somewhere on the side, so you don't get confused, and nicely draw the free body diagrams for that, right? But you can draw it on the same picture as well. So we have like this one here, we have this couple here. So this is M, this is P, and we have these reaction basically forces. Or maybe if I want to be more accurate, so I have like this guy here, right? This B, point B. And I have these loads there, right? So this is Ex, By, and this is, let's call it A, okay? Both are acceptable. you can either draw on the same pictures, on the same figures in your assignment or in your exam. But if it's getting messy and if you think you're going to make a mistake, then I suggest draw it like separately. Okay. So let's quickly see another example. So this one over here, we have a cable, and then we have a beam which has a mass m, and then we have a surface which looks like it's not smooth, right? But it is ground. So a cable, we know a cable always apply a tension. Let's call it T. And then a rough surface, we learned that it apply two loads. And again, you can call them N and F. Let's call them N and F. Or you can call them like BY and BX. But it means you choose your basically, let's stick with N and F, right? So you don't confuse with these X and Y. And don't forget that this thing has a mass, center of mass over there, then maybe this is mg. Okay, this is our free body diagram. It is ready for the next step. By next step, I mean finding these T, N, and F. That's what we plan to do next, okay? And then the last one, so it looks like a pipe or something, but it's a 2D pipe or something, and it's attached to a wall. So again, it's been fixed to the wall, okay? And this support, we know this support. We know it is basically a fixed support, and a fixed support always has three reactions. It doesn't let us to move this pipe left and right, so this is one reaction. We cannot move it ups and down, and also we cannot bend it, right? So then in fact, I have here AX, AY, and MA, like a couple or a turning resistance at point A, which we need to find out also this one. Is there any question so far? Are we good? Okay, if you're good, I'm just gonna stop here for 30 seconds and let you guys to find out the free body diagram for this one. See, I left the most difficult one. I left the most difficult one for you guys. See if you can draw the free body diagram for this one. Then I randomly call one unlucky person to explain it. No, I'm just joking. Let's see if you guys are still there or no, you're asleep. Oh, it seems everybody's still there. All right. So let's do it together. Let's first find out what it is really. Okay, so I have like a plate, like this shape. I have like a plate over here, like this plate. So let's say this is a plate, like maybe a thin plate. And this thin plate has been pinned at point A, like this is wall, or maybe a column or wall or something. And I nail this plate to the wall. So this is where I pin it there. So this is a pin then. And then what's going on over here? So this plate has a slot inside it, okay? It has a slot and or groove or whatever. And then we have this big pin, which is attached to the wall. So this black one, a large pin attached to the wall. Okay, so, and then we apply load F over here. Hope you guys can understand this mechanism. Let me show you here something. If I okay, all right. So let's say this is the plate. This is the plate that we have. It has a thickness, all right. It has a groove inside. See, I can put my finger. It has a groove. It has a slot there, and it has a hole or a pin over there, a hole, right? And now imagine if I use a pin and pin these things. Let's say I use this pin and pin it to the ground, all right? Now, if I apply load like this load F, it can rotate. Do you agree? It can rotate. Okay, this is the pin. So this is the pin. So if this one is the pin and I can easily rotate it, then it means this one can apply a reaction force like AX and AY here. Do you agree? Okay. But I'm free to rotate it. To prevent it from rotation, I need another big pin like this one, this big pin, to glue it and attach it to the ground. So imagine I glue this one to the ground. So this is fixed. My finger is there and it's fixed. So if I try to move these things now, I cannot, right? If I apply this tension, this cable apply a tension, I cannot move it. Why? Because this pin, this big pin doesn't let me. I hope you guys can understand, right? This one, this pin, if it's not there, I can rotate it. If I put this pin there, now I cannot rotate it, all right? So in that case, if I want to draw the free body diagrams, so we can say that if somebody apply this load here, like this, whatever load, F there, then this pin, if this pin, for a moment we imagine that it is imaginary and it's not there, right? It's gonna react over there, like create a reaction, right? If somebody try to apply this F, all right? If somebody try to apply this load F, then this guy over here, this apply load, and where it comes from this basically pin, okay? And this AX and AY, it's obvious. So this is the basically the free body diagram for this one. Hope it's clear. Then let's go back to our thing where we are now. Okay. All right. So this one now, if I draw the free body diagrams, we are done almost. So let me draw it over here so it doesn't get messy. Okay. So the free body diagram then is going to be AX, AY, and here we have these slot things, right? So it's going to be one over here, and then we have the external load. F, B, AX, and AY. So this is the free body diagram for this one. And I would say this one is the most difficult one, which as you can see is not really that difficult. All right, guys, so that's enough for now. We'll come back in half an hour and then we talk more. But before we leave, if there is there any question?
Yeah, so I have a question about the pin supports at 0.8. So it's not supposed to be moving, right? We can't rotate it.
Right, we cannot rotate it, exactly.
So why can't we apply a moment force? A moment reaction, sorry.
Okay, that's a good question. So Mohammed is asking, this pin A, we cannot rotate it. Why don't we put an M over here? So to answer that, we say that each pin by itself has a duty, has a responsibility. This pin A, its responsibility is just to apply a force in basically in X and in Y direction. In fact, it doesn't let this bracket to moves ups and down or left and right. Its responsibility is not it's not something to not let it to rotate, basically. Because imagine, let's again one more time move back to these things over here, right? Over here, this pin that I have, let me get rid of these forces. Okay, this pin that I have, you just look at this pin individually. Just ignore this pin for now. This pin is only responsible for not letting us to move these things left and right or ups and down. Okay, it's not its responsibility for rotation. And as you can see, I can easily move it. So when you look at one support, look it individually, isolate it from the rest and say, okay, this pin, what is its responsibility? And now remove this pin. Okay, let's remove this pin. Okay, no pin now. Everything is free. I have 3 degrees of freedom. It can go ups and down, it can go left and right, and it can rotate. What is this pin responsible for? This pin is fixed to the ground, right? Imagine that I put my finger there, it's fixed to the ground. So this pin, I can rotate these things, so it's not responsible for rotation. I can also move it like this way, this oblique way, right? I can move it. So it means this pin is only responsible for one thing and one thing. If somebody wants to move it in this direction, then these pins come to play and say, oh, sorry, I cannot let you. I'm going to apply a reaction force there, right? So then it is the combination of both of these two that doesn't prevent basically rotation. It's not just pin A. If you test something, like if you put this bracket on your wall with a nail, you nail it to the wall, you see this point A, the bracket starts rotating, right? You need another support, another pin over there. Okay? Is it clear now, Mohammed?
Yeah, very clear. Thank you.
Okay, good. Is there any other question or? So let's stop now. I'll see you in 25 minutes. Bye for now.